My name is Terrence Barkin. I'm the Executive Director of the Graphene Council, and we are the hosts for today's webinar covering graphene characterization. Everyone participating in today's webinar will receive a link to the recorded session, as well as a copy of the PDF version of the presentation slides. If you have a question for our presenter or myself, please use the chat feature or the Q&A box. So this webinar is going to cover an exceptionally important topic, and that is the characterization and measurement of 2D materials, and in particular, the material of graphene. Anybody who's worked with this material understands quite well that the way the material behaves is highly dependent upon its morphology and its characteristics, and that's why it's so important to be able to measure it accurately. Just to give you a little background on the Graphene Council, we've been established since 2013. And today, the Graphene Council is by far the largest professional and trade body for the graphene sector. We represent the entire value chain that includes graphite mining companies and raw material suppliers, graphene producers, intermediary companies such as compounders and those that are adding value and functionalization to graphene, vertical integrated companies, and end user companies. We now represent more than 25,000 material scientists all across the world from both academia and in the commercial sector. And anyone who is on today's webinar who is not part of our network and who would like to receive information, news, and intelligence is more than welcome to subscribe to our newsletter. We also work in close partnerships with very large organizations such as SAE International, the Society of Plastics Engineers, the American Composite Manufacturers Association, and many, many others, which means the Graphene Council actually reaches hundreds of thousands of engineers and specifiers and designers and producers of physical materials, physical applications and parts and solutions from all different sectors around the world. And so our mission is to act as a trusted, neutral, third-party platform to bring together everyone from academic researchers through to end users in the commercial field. And to just give you an example, we have academic organizations like the University of Manchester, of course, and Warwick University in the UK, Drexel University in the United States, Utah University, and others, as well as many of the leading graphene producing companies and end user companies like the Ford Motor Company. We have additional corporate members that are not listed here because we allow companies to join the Graphene Council but to remain anonymous for commercial and competitive reasons. So the universe of people we interact with is quite a bit larger than what you see here publicly displayed. So I just wanted to give a little orientation. Many of you are members of the Graphene Council, and those of you who are not, I encourage you to think about being engaged with us. So let's get to today's presentation. I'm very, very proud and happy to introduce someone who I consider not only a professional colleague, but a friend, somebody who's arguably the most knowledgeable, one of the most knowledgeable people on the planet when it comes to the characterization of graphene materials. It's Dr. Andrew Pollard from the National Physical Laboratory based in the UK. And Andy has put together a presentation on the different techniques and approaches to characterization of graphene materials. And I just want to give the caveat that this is not intended to be a in-depth lecture on how to do the characterization, but it's meant to be a high-level overview of the different techniques that are commonly used today, including some of the issues that are affiliated with each of these different techniques, as well as a number of techniques that are under consideration to be used, not just in the lab, but another aspect of what we want to cover today is the understanding that there is a tremendous need for graphene characterization techniques that can be used in commerce for quality control issues, for example, on batch-to-batch basis. So we're going to cover quite a wide spectrum in a fairly short amount of time, and that's why I also expect our Q&A to be quite robust. And with that, Andy, I'd love you to go ahead and take over and share your screen and do your presentation. We're all anxious to hear from you.
Great, thank you very much, Terence, for the introduction and obviously the opportunity to speak to everyone. It's great to see how many people are interested in this topic. Again, I obviously think it's very important myself, but it's great to see that you guys are all here. I'd also just like to say, it's obviously difficult times at the moment, so I hope you're all staying safe and staying healthy, and appreciate you taking the time to come look at this. So what are we going to talk about today? Well, first I will introduce National Physical Laboratory, NPL. Again, I appreciate not everyone will know who we are, and then how our work relates to graphene and 2D materials. I'm not going to go into great detail on graphene and 2D materials, as I think most of the audience will know that. I will, though, talk about an industry case study, just one slide on why this is important, why measurement is important, before leading on to what's happening in international standardization, and then get into the real meat of what I'm going to talk today, which is measurement techniques. Again, like Terence said, I'm not going to go delve into the real detailed technical parts of each technique. There just isn't time, as you'll see, but I will go over as an overview, and I will kind of try and pick out broad pros and cons of techniques, how they should be used, and also then I'm going to talk about quality control at the end, as this is a big issue that we see at the moment, and depending how much time I have, I will try and talk as much as I can on that subject at the end. So, firstly, what is NPL? Well, NPL, we're a National Measurement Institute in the UK. Essentially, you've got hundreds of scientists, technicians, engineers in one place that are focused on measurement science, so metrology, the science of measurement, in one place, but in a wide range of topics that might be looking at, for instance, measuring particles in the air for climate change, through to looking at the measurement of radiation dose in our hospitals, through to things such as nanomaterials, which we'll talk about here. We really sit in between academia and industries. That tends to be where the metrology is so important. We start taking things out of the lab, putting it into the factory floor, and because it becomes very important to really know, yes, that measurement is correct, or what is the uncertainty on that measurement? Can I compare these measurements? And we see this as a really big issue at the moment in terms of graphene and 2D materials. We work on other 2D materials, but I'm going to focus on graphene here today. And really, we have to work with both the academics and industry in this area, whether that's on collaborative projects through to pure commercial services. So again, why graphene at NPL? Well, again, we've heard many times that graphene is a wonder material. There's lots of exciting properties, and we're already seeing products come out now onto the market where a benefit is being seen from adding graphene in there. However, there are still these 4 key points that I like to talk about here, which is why we're interested in graphene. One is the characterization. How do you measure this material? I mean, it's not an easy material to measure. It is a nanomaterial. Do you have to have new techniques, or just at least methodologies? And then getting down to the development of metrology. How do we reduce the uncertainties in that measurement? And ultimately lead us to standardization, which is, again, really important. If you've got a whole supply chain that's across the world, because we know graphene, we see from the people that are here today, it's a worldwide community. We've got companies, big companies that don't want to make graphene, they want to get graphene. They want to be able to look at a technical data sheet of one graphene producer and compare that grade with another grade from another producer. They want to know, therefore, that these are measured in the same way, and that's where international standards become really important. And again, quality control, as I've mentioned. I think if we look at the issue of quality control, it's become much more important over the last sort of 3 years sort of time frame, because companies now are producing in bulk. They are producing tons per year, and they need to understand that the batch-to-batch reproducibility is good, so they can make sure that the material can go out the door and go to their customers. And at the bottom, I want to say, NPL isn't. We're not producing graphene. We're not trying to sell graphene. We're not just trying to sell a product. We are measurement scientists. So we obviously work with a lot of different people, whether that's academics, institutes, industry, to hopefully help the whole community. We do that with other big players across the world as well. So what we're going to talk about specifically here is material properties. We talk about measurement of graphene. You could be thinking electrical, mechanical measurements. They are important, obviously, for products, but typically graphene is just being added to something, so you can measure it in the same way that you would measure a normal product. What we're talking about here is the material properties themselves. So if we look at the diagram here, what are these material properties that matter? Well, the number of layers are very important. You can imagine graphite is many layers, whereas graphene is one layer. The number of layers is going to have an effect. Also, things such as real-world materials will have defects, and also contamination. Now, contamination is maybe something that can be avoided in a more academic sense, or if you're just trying to prove some fundamental science, but actually it's always going to be there when you're looking at industry and processing. So it's about being able to measure it so that you can then identify it and hopefully reduce it. So let's take an example then of industry problems. So a company that we've worked with in the UK is DZP Technologies. It's a small company in Cambridge that focuses on printing and conductive inks. So graphene is a very conductive nanomaterial. It's perfect, right? That's your company here wants to take graphene and put it into their product to make a more conductive ink. But they don't produce graphene, so they, in this case, this is several years ago now, when they take graphene from other sources and put it into their product. In this case, what they call MT46. Basically, they want to reduce resistivity of their printed film here. As you can see, they've taken two graphene materials as they were labeled. It's called graphene A and graphene B. Graphene B here does reduce the resistivity, so that's what they want, but not really a substantial amount. Whereas graphene A does, and say, okay, great, that's great. Maybe just graphene A is a good supply or a good material that we can use for our product. That's good. We'll use that material. Let's put it in one of our other products. In this case, PSS, which is a very conductive polymer, and as some of you will know. And again, so if you look here, graphene B, it's a little bit worse, but it's within the uncertainty. It hasn't really affected it. Whereas putting graphene A in there's actually made it worse. It's increased the resistivity. It's the opposite effect of what we wanted. Now, this is just a project that we did with this company to understand for them, how do the material properties affect the performance of the product. So as you can see here, actually, not all materials are the same. In this case, also, they had completely different effects depending on what product they actually put it in. And this is why understanding the material properties is really key, but also being able to compare different materials. So you can go, yes, that's the type of graphene, in inverted commas, graphene that I want to get to put into my product, because I know it's got the properties that I want. So let's think in terms of international standardization then. So again, we need to make sure that everyone's measuring it the same way so they can report it the same way, so you therefore can compare things the same way. So this is done generally through international standards organizations. In this case, I'm going to talk about joint standards that are produced by ISO and IEC. Now, these red ones here are ones that are already published, but there are other ones under development as well. And the first really key step was a terminology standard. Now, I'm not going to go into this, but it was published in 2017. This is really just to understand the language that everyone's using, academics through to industry, that we can talk the same language. So we know that if we're asking for graphene, or we're asking for graphene oxide, or we're asking for few layer graphene, that we know that what one person wants, we know what that is, because we don't confuse the type of materials. This is really important. So again, that was published in 2017, and actually last year then there was another standard that was published that was actually a technical report. So this is informative. It's not normative standard which says you shall do this. The informative standard is essentially giving information for users, industry, to make better decisions. And this is a technical report on measurement, and I'll go into that in more detail in a minute. But essentially it's given a guide of the type of measurements that you can do. So these are published, but there's then standards that are being developed at the moment. And unless you're doing this standard development, it's typically you don't tend to see that this is happening. So as you can see from here, there's three standards that I've put here. These are all what I would call flakes. Now, again, going back to this, there's different types of materials. There's really are different forms. Now, if you say are trying to make a composite, for example, that might want a powder or some kind of dispersion. So essentially you're looking at particles, you're looking at flakes to add into that composite. However, if you're looking at, say, an optoelectronic device, you might be looking at a graphene sheet, a single layer of graphene covering a substrate. And that's what I would refer to as sheets today. And not really covered in this talk so much, although I will point to it as we go. So one covering here with these three are the flakes. And at the same time, although we have something that we might call graphene, there's also, for those that already in the community know things like graphene oxide and reduced graphene oxide. So actually we need to have a standard to determine the difference between graphene, reduced graphene oxide, graphene oxide. We need to understand the chemistry, and this then allows us to be able to use the right structural characterization analysis for whether it's graphene or for graphene oxide. What I'm really focusing on today is this standard here. This is structural characterization of graphene flakes. So again, the powder, something that's graphitic in there. However, the techniques do then apply to geo as well, and I will touch on the chemical characterization. There is a standard that is being developed for the structural characterization of CVD grown graphene. Again, I'm not going to talk about specifically, but the techniques in there are also detailed in here, so I will point that out as we go along. So this is the kind of standardization landscape where we are at the moment. So looking at the measurement technical report that I said about, this is actually a standard that was published last year and was led by our colleagues in the US and Korea. And this is a really nice, this figure here, understanding of what measurands can be measured by which techniques. So again, down the left here, you have these different measurands that are important properties of the material. And on the top, you have the techniques that can measure those measurands. So again, this is just a guide of, you know, what can you do, what techniques could you use. And actually in the document, it also describes each technique, each measurand, also talks about the pros and cons. So this is a really nice start and a source of information there. And I would, you know, if you do have the opportunity to look at the standards, it's a very good one to get an understanding of this area. However, that's not a standard to say this is how you measure this, and you know, a protocol to say this is how you measure this, and this isn't a standard way of doing it. It's a guide of different techniques. There is no currently published international standard on how do you measure the structural properties of graphene. So to plug that gap, NPL do a book series, a good practice guide. We did a good practice guide in collaboration with the University of Manchester on the structural characterization of graphene. Now, it actually comes in two sections. Essentially, one section is on the flakes, as I keep saying, these flakes, these powders and dispersions. And then another section is on CVD grown graphene, a graphene sheet on a substrate. But again, I will focus on flakes primarily here. Now, really, the idea of this good practice guide was to put an interim source for how people can measure graphene. Whilst the standard is being developed, we needed something out there so that industry could use it in the interim. Again, it's not a standardized protocol in any way, but it is a good practice guide. And you know, still at this moment a good source of a method to measure these properties. Now, not only does it talk about the techniques, which techniques to use, the decision tree, your kind of flow diagram, how the techniques complement each other, it also does have specifics on the protocol for not just the measurement, but also the sample preparation and also the data analysis. So again, this good practice guide is then being used as the basis for the two standards I showed before of the structural characterization of graphene flakes and graphene CVD graphene. So let's look in a little bit more detail. Again, here you have the kind of what I'm talking about here, these graphene flakes are kind of in a powder or some kind of liquid dispersion. So here's kind of one of the main figures where we're talking about the flow chart, the decision-making tree you've got to go through here to understand how I should measure this material. If you get someone giving you essentially this black box for the material in, what should you do? How should you measure it? What are the decisions you get to make here? And what techniques do you use? So actually, very simply, you're kind of going through an initial step to check with Raman Spectroscopy. We'll go into detail on all these techniques in a minute. Using Raman Spectroscopy to understand that this material is at least graphitic, before then doing a sample preparation to isolate flakes. You can look at the flakes, isolated flakes or particles themselves. Therein is a decision here whether you go down the route of using TEM to do these measurements, or a combination of other techniques here. But ultimately, what you're trying to get is to understand the structure, right? You're trying to understand, you know, what are these particles like? What's the sort of sizing, the thickness, the disorder that's present there, which is, again, is a very important property as we'll go through. So let's start with Raman spectroscopy. So what is Raman spectroscopy? Essentially, it's a technique that is an optical method, essentially shining a light laser onto a material and looking at the light that's scattered. But in this case, Raman spectroscopy is generally seen as the go-to technique, I would say, for carbon nanomaterials. It's a very powerful technique, but it's not going to give you all the information in just this one technique. However, it's quite quick, as it's an optical technique. It's quite a fast measurement. And what you're getting out there quite quickly, if you look at the spectra below there, essentially when we're looking at these spectra, we're seeing that we've got sp2 hybridized carbon. We're seeing there's some disorder in there, but we're seeing that generally it's a graphitic material. And from this technique, you can pull out measurands such as, again, the sp2 versus sp3 content, the level of disorder or defects, and also the number of layers. However, there's a big caveat in this technique in that because it tells you many things, you have to be careful how you interpret the data. So actually taking, again, a black box and just a material and doing the measurement isn't necessarily going to get you the understanding that you need, and hence why we talk about these complementary techniques. Also, you have to be very careful determining between measurement of a powder, so like more of a having a bulk powder and doing a measurement of the surface of that bulk powder versus measurement of individual flakes. Now, going back to the flowchart that we just saw, in that case, the first instance, you're just looking at the powder to see is it graphitic. But later on, you can then also look at isolated flakes if you need to understand the number of layers specifically. But again, it's a really big difference between those two that you have to be really careful. And I'll talk again a bit more about the quality control at the end of Raman spectroscopy. One of the options then is to, we say we've isolated these flakes on substrate, is to then look at microscopy. Now, one of the routes uses SEM to start with. So scanning electron microscopy is essentially using, again, you're bombarding the surface with electrons and looking at the scattered electrons to get an image. You can see these images down below here, very high resolution nanoscale images here. And what we're getting from this technique, though, is the lateral flake size. So again, you can see we have flakes here. We have finite-sized, lateral dimension-sized particles. In this case, the shape of flakes. However, generally, we don't get flakes that are all the same size, right? You tend to get a range of flakes. So not only are you trying to get an understanding of lateral size, you're trying to get understanding of the distribution and range of lateral sizes as well. You can't really just give a value of this is the lateral size for my particles. You've got to understand the range, as it can be very different between products. And if you see here on the right, on the top right, you can see these very different distributions of lateral sizes of these flakes when you look at hundreds of flakes with this technique. And again, if you look at the bottom here, taking our example of graphene A and graphene B from before, that although these look similar, the scale bar is actually an order of magnitude different. So again, there's a very big range here depending on where you get the material. So now, a big issue with this, of course, though, when you see a lot of SEM measurements they might look like these here, the graphene A and graphene B. That's a great to get an understanding of, what does the morphology look like? Does it look like a flake or spheres or scrumpled up? What does it look like? But actually, what we need to do in our protocol is get the sample preparation correct, so that we can essentially isolate the flakes, so we can then measure the lateral size, so we can then produce this type of histogram here. So following on from the SEM, then we've got an idea of lateral flake size. We then want to look at the thickness. That's where atomic force microscopy comes in. Now, AFM is a scanning probe technique. So essentially, you're taking a tip that's got a nanoscale sharpness at the apex, and you're moving it along a surface to understand the topography. And you produce an image like this here, where the brighter areas are essentially higher. So you can see that there's three kind of features there. By using this technique, we can actually determine lateral size like SEM, but also then the thickness. Now, I'm not saying number of layers, because that's not really what you're actually measuring with AFM. You're measuring the thickness, which can be related to the number of layers. And actually, by looking at individual flakes with Raman spectroscopy, you can get your complementary information and validate that these flakes are the number of layers that you believe them to be. Also, you can imagine there's issues around this technique with things such as contamination, comparing the thickness to number of layers. And also, actually, in terms of speed, this tends to be a bit of a bottleneck when you're trying to measure these flakes. It's a slower technique than SEM, and definitely slower than Raman as well, Raman spectroscopy. So one of the ways of getting around that is to look at correlations of lateral size versus thickness. Now, not all materials have a correlation between lateral size and thickness, but a lot of them, or most of them, do, because of the way that they're produced in a top-down way. So that means you can get this relationship between thickness and lateral size. At the same time, there might not be a correlation, so it does go back to looking at essentially hundreds of particles to get a statistically relevant sample. At the same time, both for AFM and SEM, you could see why the sample prep becomes so important, because if you do not prepare the sample in the correct way, not only can you get a good, you can't get a good measurement of the thickness because the flakes aren't isolated, but also if you can skew the results of what you think the material is depending on how you prepare the material. So some preparation methods don't work because actually it removes parts of the size distribution. If you think of that graph, it might be that bigger or smaller particles are removed. So that's one way of looking at through those selected techniques, but also in the standard we do talk about TEM as well. So this is transmission electron microscopy. Again, it's bombarding surfaces with electrons and looking at the scattered electrons, but it's a very high resolution technique. Typically, TEM is is more expensive than the other techniques, and it's generally needs a higher level of expertise, and also quite difficult in terms of sample preparation. So there are those caveats with it, but it does give you a lot of information about these flakes. And as we can see here, in the top of looking at essentially single layer graphene flakes and bilayer graphene flakes, you can understand what the flake looks like and the lateral size, but also then you can understand the number of layers as well by looking at the diffraction pattern, which is so a very, very powerful technique in that respect. But again, microscopy techniques, we will need to look at, again, a statistically relevant amount of particles, flakes, to get a good understanding of the material. So again, these are the techniques that you saw in the good practice guide, but how does that relate to the standards? So there's a structural characterization of graphene flake standard that's due to be published this year. Obviously, with the way things are at the moment, you can't be too committal about that date, but essentially it's been now been accepted for publication. So we're going to have a measurement standard that's an ISO/IEC standard saying, okay, here's the process to measure these materials, here are the protocols to use, and here is the your decision tree to essentially pick which techniques you're going to use out of these, follow these protocols so you can produce these values and uncertainties for the measurands. And the uncertainty is very important here as well. We're not just saying here's the value, we've got to say here's the uncertainty in that value too. So if we look at the current draft of the flowchart, it looks very different to the one in Good Practice Guide, but essentially it's the same, except that here we have BT as well. So this is a measurement of a powder that's in the standard, and again, it's an important, powerful technique that isn't the Good Practice Guide, but is in the standard. So what's this technique for those that don't know it? Oh, the BET method, or the Brunauer Teller method, is essentially used to determine the specific surface area of a powder. So it's a bulk technique. You're essentially putting a lot of powder in a tube, and you're essentially absorbing gas molecules onto the surface of that powder, and then calculating the surface area from that. Now, again, it's a very powerful technique. It's not, I wouldn't call it a fast measurement. It's not Raman spectroscopy, but it's not as slow as saying doing hundreds of flakes with microscopy methods necessarily. But again, as it's a bulk technique, you have the power of looking at the powder as a whole. And that gives you this specific surface area. And this is actually a very important measurand. If you look at, say, the batteries area, you have carbon materials in the batteries being used for energy storage. Specific surface area, SSA, is an important measurand that companies want to understand as it affects their performance of their batteries. At the same time, there is a big issue of what you can determine from this material. Now, from this technique. Now, you can determine the SSA of a powder. That's what the technique is for. But in a lot of cases, people will use that to try and calculate the number of layers, and that doesn't work. Essentially, theoretically, you could look at these values. So again, if you had this very high value of 2,630, you could argue that could correspond to individual graphene in theory. However, in practice, there's other variables that affect it. You generally get restacking of these graphene particles, graphene flakes. So actually, you can get particles that might be very thin in the primary particles themselves, don't have many layers, but actually the specific surface area can be quite low because of this restacking. Whereas actually other materials then that may be more defective or have more sp3 content can have a much higher SSA value. And this is actually because of, as we see here, we have the non-graphitic versus graphitic ratio. Generally, you see this trend of higher surface area with higher amounts of non-graphitic material. So this is, again, a powerful technique to look at, and it's a good way of comparing different materials and even the same material batch to batch. And BT will vary depending on several measurands, but again, it's about taking the SSA, that's the value that you take away from using this technique. So going back to the landscape that we looked at earlier, again, we've really here talked about the structural characterization of graphene flakes. Now, if we look at graphene oxide, the SEM and AFM is applicable there as well in the same way. And if we look at the structural characterization of CVD-grown graphene, the standard here is actually using Raman and TEM. Now, not in the same exact same way as I've described here, but it's using those techniques and the fundamentals of those techniques to allow the understanding of the number of layers and coverage of CVD graphene on a substrate. But again, I mentioned before, chemical properties are really important as well. Actually, if you look at things such as composites, many different application areas, the chemistry, the surface chemistry particularly, will play a really important role in how well the material improves your product. So this is very important for us to not just determine the difference between graphene oxide and reduced graphene oxide, but also to give us an understanding of that chemistry to relate it to how the products are being improved. Now, as I said, the structural characterization of graphene flakes, 21356-1 is going to be published this year. The chemical characterization standard is further behind, so we'd be looking still probably a couple of years till that is published. But it is being developed, and so we can say the techniques that are being used. So within this chemical characterization standard, again, if you're taking your black box, you're taking your material, you're given this material, we're looking at a combination of techniques to really fully understand the chemistry of these materials and how they differ. So XPS at the top here, X-ray photoelectron spectroscopy. Again, it's a reasonably expensive technique. It's done under a vacuum. You're essentially bombarding the surface with X-rays and looking at the photoelectrons that come out to understand the chemistry of the sample, and it is surface sensitive, but it tends to be a very go-to technique for understanding the chemistry of these materials. And so you get an understanding of the elemental composition. If you're doing the XPS correctly and calibrating it correctly, you can get very quantitative information. It also is very good at determining the carbon to oxygen ratio, which is a key measurand to determine the difference between, say, graphene and graphene oxide. And so this is very much a go-to technique, but at the same time, if you have highly functionalized graphene, FTIR is very powerful for understanding those functional groups in more detail. Other than just the carbon and oxygen ratios and bonding, you can get a better understanding of the chemical, the functional groups that are present. And TGA, which is a bulk technique, essentially is heating up a material and seeing the weight lost with temperature. This gives you not just an idea of, say, moisture content, but gives you an idea of weight percentage of the chemistry as well. So that's, again, very complementary techniques to be used together to get a better understanding of the material. And ICP-MS is a technique that's essentially used for looking at trace metals in here. So again, that can be very important for, depending on the type of application you're looking at, it can be a very important measurement for understanding the trace metal content as well. So really the standard is about how to use these techniques and the protocols, but also how to use them as a kind of holistic view of the chemistry as a whole to complement each of the techniques complement each other. So one technique that I haven't mentioned that isn't in these standards, but is a very powerful technique, is X-ray diffraction, XRD. Again, this is used a lot in industry for different applications, but generally you're looking at the crystallographic information. You're essentially looking at diffraction of the a diffraction pattern of the X-ray beam. And this is actually used as a tool to look at crystallinity. And if we look at things such as the EU REACH regulation that's now changed and is new from January for nanomaterials, this is a very important technique for looking at crystallinity. I think it's a good example. And it is a bulk technique. Again, it's relatively fast. It's not, say, the speed of Raman Spectroscopy, say, but it's a bulk technique, and it's, say, faster than, say, necessarily doing microscopy. But there's a big issue again around just using this technique on its own to understand what the material is. Really, you need to have complementary techniques again to really understand. So maybe similar to Raman, that can tell you several things, your disorders as an example, but it does have its caveats that it needs to be really, if you need to understand the material fully, you need to be looking at complementary techniques alongside XRD. So a really important thing then to say on top of all of this is that when we're standardizing these materials, it's really important that it's underpinned by metrology. What does that mean? Well, it doesn't mean that we've just done a measurement somewhere and said, okay, well, let's standardize this. What it means is that we've validated these measurements. And we do that through international round robin and inter-laboratory studies, where essentially we take the same material, the same protocol, and measure it at labs across the world, and essentially then look at what's the variation is of the values that we get. Now, this is because it's always different between labs, and that can be for many different reasons, but essentially it gives you an idea then as a end user. If you see that technical data sheet, you know it's been measured to a standard. Now, it might be that one lab reports that their uncertainty is X, but actually you know that if you're going to compare it across different technical data sheets that are measured by different people, there's going to be variations. So you really want to know if you've got a value of one flake, your one material is, say, 100, and another is 200, let's say it's lateral size, 100 and 200 nanometers lateral size. Well, is the uncertainty on that measurement 10 nanometers, in which case they're different, or is it 100 nanometers, in which case they're essentially the same? That's really important for end users. So we do this inter-laboratory studies through VAMAS, and actually there's a new technical area called graphene-related 2D materials that's co-chaired by myself and my colleague at NIM in China, Dr. Ling Ren. And now there's actually 7 experimental products are underway. And you'll see down there different techniques that I've already mentioned. So these are so that we can essentially validate these measurements, so that we then, when we put them into the international standards, we have an understanding of if the protocol works, issues around it that we need to understand, and essentially what's the kind of variation will be across labs. So this validation is really important. I want to talk about, in terms of validation, NPLs, like I say, we work with lots of companies. We do lots of commercial work with companies, doing measurements for them to better understand graphene, of course, lots of different things, but in this case, graphene, we're talking about to understand really what that material is like. There might be advanced measurements we need to develop, but we can provide test reports to say that this is what the property is and the uncertainty on that, and this is by using validated methods. This is really important. But also, we actually lead part of the Graphene Flagship validation service. So Graphene Flagship, for those that don't know, is essentially a European initiative of over 150 participants, 1 billion euros over a 10-year project. And within that, there's a validation service that's actually free of charge to Graphene Flagship members, but essentially is a place that users can go to, or participants can go to say, okay, I need a validated measurement of this measurand for this material. And so this is something that's led by NPL and alongside LNE, the French NMI, and the University of Zaragoza in Spain. And this is a service that actually is provided outside of the flagship as well, but it's very much going, okay, give a material you want to measure around, here's the property, and here's the uncertainty. And and talking of which, I'm sure Terence can talk more about the Graphene Council service. That is a different type of service. It's more not about the validated measurements. It's about verifying and by an independent source graphene producers, and that does then use NPL's capability for the measurement part as well. So last bit I want to touch on, and last few minutes that I have, is quality control. So this is really important. I've talked about it a lot. But why is it important? Well, if you think you've got now companies all around the world that are producing tons of this material, we talked about powder today, you've got tons of powder that are being produced every year by each company. You really need to make sure that this product that's going out your door is essentially as similar as it can be. So you need to have some understanding of what the variation of your batch-to-batch reproducibility. You need to understand how much does it vary, how much can you accept before it goes out that door, and actually the testing therefore becomes very important. One company we worked with said that 40% of their cost was actually related to storage of material, because they can produce so much. Essentially, you end up with barrels of this black powder, and they check it before it goes out the door, and they have to get a sample sent off to another lab and get results back in 2 weeks. Obviously, not only is there a cost associated with the testing, there's a big cost on the storage, and also if you get a value back, you get the results back that say, no, this isn't good enough, you've then got to get rid of this room full of barrels of black powder. So it becomes very important to have fast techniques that can be done on the factory floor, and actually that can be done by a technician. You don't want to have to go and find a professor of Raman Spectroscopy or scanning electron microscopy every time you do a measurement. You want to have an understood protocol that you can follow, that's is quantifiable, and what the uncertainty is. And so essentially something that you're going to get either maybe offline in several minutes, or inline, so kind of in seconds. So this is very important. NPL, we've been looking at this with different companies. There are techniques I've already talked about that you can see as using for quality control. Raman spectroscopy is kind of a key one, and that's actually a fast technique because it's optical and you get a lot of information out. However, quantifying what it actually means isn't necessarily something that you would be doing. All you're really looking for is understanding the change. Now, if we look at here, we call the metrology pyramid, it's really therefore important that if you have these measurement techniques, you have a lot of them. They're used, let's say one of them is in each factory, and you have a lot of these techniques that aren't necessarily very accurate or precise. You're essentially going to have that traceability to the top of the pyramid here, where you have a few places that can do very accurate, precise measurements. And this is what I've been talking about really today, is the standardization of this top of the pyramid, where we have these techniques that you're not going to perform on every batch, but you are going to want to perform to understand what your material is, and give you hopefully very accurate and precise value for those measurements that you're interested in. And then you can use those techniques to validate your fast quality control procedure at the bottom here. Now again, that could be something like Raman spectroscopy. It could be something, as I talked about, your BET or XRD is techniques that are bulk techniques, and again, they're not necessarily as fast as an optical technique, but they're not as slow as, say, a microscopy technique. Again, as long as you understand what the change means in these values that you get from those techniques, and you can kind of quantify it by validating it off of the top of these very accurate, precise, but expensive and time-consuming techniques. This is really important. There's a few examples there of different techniques that people do use for quality control to try and help them understand that. But they're not the only ones. And typically, what we see at NPL, a lot of companies using actually nanoparticle sizing techniques. So none of the ones that I've talked so far, but what we're talking about now are maybe reasonably faster and cheaper. We're talking, say, a few tens of thousands of pounds or US dollars, things that you can buy and essentially put the sample through and get a value out. Now this is really good because they're generally the sort of thing that we're talking about. You could have one run by a technician. You could have one instrument in the factory. You essentially take a sample from each batch before it goes out the door. However, there are difficulties around that. Now, if I just bring the example of DLS, which is dynamic light scattering, it's well understood that techniques such as DLS and other nanoparticle sizing techniques essentially they are modeled on using spherical nanoparticles. They're not there, they're not there to really, or at least yet, understand non-spherical particles accurately, quantify that. And also they tend to give larger particles more weight. So if you've got, as you saw at the beginning, this SEM distribution of lateral size, actually with a nanoparticle sizing technique, you see, because of the way they fundamentally work with light scattering, you see that there's a more of a skew towards the larger sizes. So that can therefore give you spurious results. If you take a technique such as nanoparticle sizing techniques, sort of DLS, etc., you can end up having a wrong result if you take it quantitatively. I've seen instances of reports of particle sizes that are maybe not just one but 2 orders of magnitude out. So it's something that can be, again, maybe good for quality control. It can show you differences, and then when it varies enough, you can go, oh, okay, there's something wrong here. We need to go back to the top of the pyramid, do those accurate measurements to understand what's gone wrong, or we know that we can't send that product out the door. Because again, there's another issue with techniques such as this that's around reproducibility and actually repeatability. Even taking the same technique, so the same instrument, the same person, the same sample, you can get a 40% variation in the results. So again, it's something that has to be really taken into account when you're using these techniques for quality control. They're probably good for in-house understanding of your batch-to-batch reproducibility, but not necessarily for quantitative assessment of measurands to then report. Okay, so I mean, just to summarize that then, it's really important that you understand the structural chemical properties of graphene and all 2D materials, because they directly link to the final product performance. And really, what we're trying to address here with the international standards, these measurement standards, is what is my material, the type of procedure that you would follow to understand what is this material, what's these fundamental measurands, and to what's the uncertainty related to those values. Now, these ISO standards, which is a graphene terminology standard, are very important for consistent language, but then also for being consistent across the supply chain, that people can compare different data sheets from different companies when they know that they follow a standard, an international standard. And at the moment, the good practice guide is out there for users to use, but this year, it looks like we should have this international standard published for the structural characterization of graphene flakes, at least. Again, I just talked about quality control. This is really important. We know it is to industry. There are no standardized measurements for quality control at the moment, but with a standardized measurement for structural characterization of graphene, you can then look at validating other quality control methods for at least in-house protocols. But ultimately, metrology is really to instill this trust between the community, the graphene community, that's the producers, the end users, companies, researchers, and that's where metrology is here. And hopefully the reason that you guys are here is because you think it's important too. So with that, I'd just like to thank my collaborators from NPL and externally, as well as the guys that have funded me, and for all you guys that have turned up to listen to me. Thank you very much.
Well, Andy, thank you so much. On behalf of the Graphene Council, we're extremely pleased to be able to present this to the community. I think this was really needed, and you've done, of course, an excellent job on presenting what is an enormous amount of information in a really short period of time. So thank you for that. I do want to just go ahead and make one small presentation about the Graphene Council before we go right into the Q&A while I have everybody's attention here. And then we'll come back to Andy. So just briefly, again, for those of you who are not familiar with the Graphene Council, we just recently, just last month, published a report called the Graphene Report, which covers graphene production methods, as well as the characterization and techniques, much of what you've seen today. We talk about these many different types of commercially available graphene materials. Dr. Pollard referred to that. There are many types of graphene materials, including graphene oxides, reduced graphene oxides, and then it comes in many different forms, including not just the powders, which we kind of focused on today, but also in solvents. It can be in a paste. And then on the CVD material, that's an entirely different market as well. We talk about standardization, applications, commercial market pricing, and a profile of 200 graphene producers worldwide. So that's just what's in the Graphene Report. And what's more important, or what's equally important, is we really encourage you to consider joining the Graphene Council. We have memberships for both organizations and individuals, and that includes universities and commercial entities. That includes then a copy of that graphene report. We have, as I said, membership for an individual, for a university, which then covers all of the university staff and students to have access to graphene intelligence, including a weekly graphene intelligence briefing, which covers research developments, commercial developments, and patent filings worldwide. So all that is in there. And then the last commercial I want to give is just for a webinar that we're going to be holding next Thursday, so 2 days from now, on CVD and monolayer graphene specifically, and we're going to have presentations from LG Electronics, General Graphene, and Groltex as part of that presentation. So you'll receive a link to that. Many of you who are registered for today, I know, are registered for Thursday's webinar, but we'll make sure that you get that link as well. And so let's go through, and Andy, if you don't mind pulling up maybe your last slide.
Great.
Okay, so thank you for pulling it up. And let me just, like I say, I'm going to run through some of the questions here. So as I start to get through that, you mentioned in particular, I think what's interesting for many of us in the commercial world is the ability to use some of these measurement techniques for quality control. And I know you and I had spoken before about the fact that many companies are using either Raman by itself as their primary quality control measurement, or BET and surface area, and using that as a proxy for the layer count. And you mentioned that both of these have their limitations. Can you just talk a little bit more about that, about let's say the weaknesses, I guess is the best expression, of relying on just one of these techniques as your primary quality control measure? That silver bullet is a combination of a couple of these that can be used for relatively quick, relatively inexpensive quality control processes for companies that are producing large quantities of the material. Are there any recommendations on what a good combination might be? And I know there's no silver bullet to this one.
Yeah, no, there's definitely, in terms of quality control at least, there's a lot of factors, not just the scientific factors. Of course, I mean, the reason why you have quality control techniques and you don't do the in-depth characterization that I've talked about on every batch is it's just not cost effective. There's no way that a company would be able to do all those measurements. So I think it is, like you say, trying to do the most that you can. So if we think about quality control, Raman Spectroscopy, again, is a very fast technique. There's a lot of pros with Raman Spectroscopy. I think the main issue around that is not trying to take anything quantitative from just Raman Spectroscopy. What's most likely to be looking at a powder. You'll definitely get some information from there, and if you see variations, you can then determine what your tolerance is to those variations. But I wouldn't take from it a Raman spectroscopy measurement of a graphene powder or powder containing graphene or full layer graphene. I wouldn't take that measurement and then try and assume something quantitative from it. Same with BET. The SSA is a very important metric for a lot of application areas. As you can see, it's in the standard itself. As definitely industry thought it was very important to have that there. There's known issues around BET for quite a while, I would say, in terms of that value not necessarily representing the particle size, and that's because of agglomeration and aggregation. So again, I don't think that you can determine the number of layers from BET on its own. You would really be determining it from the other techniques and then using BET to go, okay, that relates to this specific surface area. And then if you were to do quality control with BET measurements over time, you would see if that varies, that you've got a variation. You may not know what that variation is, but at least you know that the product is changing and you need to address it in some way. So in terms of techniques to multiple techniques to use, I think it's difficult. I know a lot of companies do use nanoparticle sizing, and I think again you do get useful information of changes in there, but again that's structural. As an example, if you needed to look at the chemical changes as well, you would need a different technique typically. And something like Raman spectroscopy can tell you the level of disorder in there that can be related functionalization. So it might be a combination of, say, Raman and a particle sizing technique to give you an understanding of the structural and chemical properties.
Excellent. So there's another issue here, and that is for companies, when they're selling their materials, they usually include a material specification sheet as well as like a safety data sheet. And one would assume that there's quite a bit more analysis that goes into determining the measurands and the numbers that are provided on the specification sheet. And then, of course, they can't do the same number of tests or the degree of validation and characterization on the batch to batch. So, the validation service you mentioned, I think, is really, really important, both from the producer side as well as from the consumer side. That was really the initiative that we had when we did and launched the Verified Graphene Producer Program. Was we were looking not just at the material, and we thank the NPL for the extremely competent service they provided in the characterization of the material itself. But of course, producers, especially with graphene, are not producing a commodity material. They're often changing that material, and many times it's bespoke material for a particular customer. And so I think there was a point that you raised about distribution, and we have one of these questions about how do you know and how do you measure the distribution? Because normally a graphene material, it's not going to be all 3 carbon layers, 100% 3 carbon layers. It'll be a certain percentage at 3, some at 5, some at 7, some at 12 or 15 or whatever the case might be. So can you talk a little bit about how to measure for distribution? And if it's appropriate, we also have other questions about how do you measure for the lateral flake size? Because of course it's not just distribution and layer count, but distribution and lateral size as well, which all have an impact on its performance in an application. Does that make sense, those two?
Yeah, and I'll try and keep my answer sorry briefer than last time. But there's a range of lateral sizes. So you're looking at hundreds of flakes to get a statistically viable amount of data, and you're therefore looking at essentially a median value of that distribution, and then looking at a standard deviation from the mean as a way of understanding the range. That will change depending on if you've got a very tight, say, histogram. If you think back, sorry, I can control the slides here, I think. If I try and go through, if you think about the distribution here, the values, what you'll get from the median values of these two distributions will obviously be different. But then also you can essentially, by looking at the forward half maximum as a kind of distribution here, you'll see that there's a very different range, and that will come out essentially by looking at the standard deviation from the mean here. So that is what you would do for when you've got hundreds of measurements, and you can do that with AFM if you've got hundreds of measurements. But otherwise, if you're relating the thickness to the lateral size through AFM, then you would essentially take from here the range that you see in lateral size and essentially calculate it for the thickness as well.
Excellent. We have another question, and it's about terminology, and that it took literally years just to get to an agreed terminology, and even when it was published, not everybody was fully satisfied with that, simply because we have this, let me see, how do I express this? Depending on to whom you speak, and you say you have graphene material, a purist would say the only thing that's graphene is a single carbon layer material, and anything above that is not graphene, it's something else. And then we have the accepted ISO standard up to 10 layers to be able to call something a graphene material. But of course, there are materials that have more than 10 carbon layers, but they have commercial value. And I'm not sure if you have an opinion on this one, but do you see, we now have graphene oxide, reduced graphene oxide, graphene nanoplatelets, graphene nanoribbons, CVD graphene, monolayer graphene. Some people even refer to pristine graphene as a substitute for single layer or CVD graphene. Do you see the vocabulary actually expanding and we come into even more grades or descriptions of material? Or is that too dangerous an area to discuss?
Well, so it's as you say, this was many years in the making. The terminology standard and it took a while to get consensus, and that's what standardization is. But it's trying to also get a balance between what you might use scientifically and what industry uses. Now, graphene has been defined for actually a while before the standard came out, and graphene is a single layer. But it's appreciated that there's material out there, that these powders might be called graphene material. Essentially, it's few layer graphene. This is where the issue came from, that graphene was a theoretical substance, and then when actually people, Andre Guyman and Kostrin Vasilov in Manchester isolated it. Since then, we've had his bilayer graphene, his trilayer graphene, and his few layer graphene. The real issue was, where does few layer graphene stop and graphite start?
Mm-hmm.
You can't have 300 layers of graphene. I think that is few layer. It obviously seems nonsense, but that was what was being used at the time before the standard. So standard is there to try and help with that terminology, but each international standard comes up for review, depending on the type of standard, every sort of 2 to 3 years or so. And the terminology standard will start to be reviewed this year, to then looking at a new edition, essentially. However many years. So I agree there's other terms that can go in there, and we see that the community is growing constantly, and so there may be more terms that need to go in there. But again, it's balancing on not just calling something because it's a useful way of talking about it. It's about still trying to be based in scientific fact, at least.
Absolutely. Well, I think we're in a good way. And of course, the Graphene Council is a party to the standards development. We're part of both the ANSI, ISO, and the IEC standards working groups. And so we're able to contribute to this discussion. We do have a question about sample preparation for Raman measurement, but I would argue that sample preparation techniques being consistent are important for all of these measurement techniques. You want to just talk, I know you mentioned it already, but not to miss the importance of sample preparation and how that will affect the outcome of your measurement techniques.
Completely, yes, completely. It's not just about the measurement, and the sample preparation and the data analysis are as important, because you can have a large sources of uncertainty in the sample preparation or data analysis methods as well. So again, yes, the good practice guides, these standards themselves, they do talk about the sample preparation, and not just to be very specific on how to isolate flakes, but the fact that you are isolating flakes on a substrate. For instance, you're not doing SEM of a big agglomeration of particles and trying to determine the size from that. You do have to fundamentally try and prepare it so you can isolate flakes, and so that you're not removing in some way a significant section of that population of sizes. So sample preparation is really important, and is in both the good practice guides and the standards. Yeah.
Exactly. So for those of you who are interested, the good practice guide is available publicly. There's no charge for that, if I recall. Is that correct, Andy?
Yes, it's free on the NPL website if you look at Graphene Guide. Yeah.
Yeah, so that'd be great. And of course, the Graphene Council, part of our mission is to connect and network people and to put one scientist in touch with another. So we encourage you to engage with us, so we can, if you have questions like this, we can put you together. I would even argue that the nomenclature is important, because of course in the commercial world, and this is where I think we really bridge two interesting worlds, and we're so appreciative to have you from a national metrology center. And we have many academics on this call, but we also have many commercial people, and these are really two different worlds, if you will, where in the commercial world, basically there are companies that are calling anything that has some carbon in it a graphene. And the end user community, I can tell you, because we interact with many companies who are either large OEMs or they're intermediary companies, and they want to use graphene in their applications, say in plastics or in battery technology or sensors or films or whatever it might be. There's more than 45 major vertical markets we've identified. The end user community just hears graphene, and they don't understand the nuances between the different types of graphene materials. And I would argue the nomenclature is important, but even more important is the topic we're talking about today, is to consistently understand how to measure any given material that's a nano or a 2D material. And because it's that characteristic that determines its performance in a given application. So I think what you've presented today, and I think the work of the standards bodies on understanding a standardization to which techniques to use. And then the flow chart is also quite helpful to kind of cascade where, you do an initial measurement, and if you see that it doesn't have a graphene signature to it, or it doesn't appear to be the right material, you don't go and spend money on stuff that's not going to give you a good outcome. So I think that's been quite helpful. We do have different questions coming from the audience one is about cytotoxicity of graphene, which I think is beyond the scope of this particular presentation. And then you mentioned today's focus was really on the structural characterization of this material, which is quite important. You touched on the chemical composition and the use of XPS and other techniques for that. We haven't talked about the conductivity testing, and I don't know if you want to touch on that at all, but we didn't talk about, like a 4-point probe test for conductivity and some of the issues there with, for example, to do the 4-point probe, you have to take a powder, compress it, and then did you change the characteristics such that it makes the measurement, is it still relevant? Do you want to take a shot at that one?
Sure. I mean, just on the terms of kind of nanosafety area, we won't talk about nanosafety, but measurement becomes very important when you've got so many different types of material that if one is going to cause an issue and another isn't, you need to understand that material beforehand. So I think that's something that's been in the nano arena before graphene, that's been an issue. In terms of, electrical properties. So this is a bit different really to the structural chemical in that you're looking at fundamentally what is the material, because ultimately if you're gonna take a powder, really it doesn't necessarily matter what the electrical conductivity of the powder is. It's about what you do with it, right? So stuff like the electrical properties, mechanical properties, thermal properties, a lot of the time it really just matters what you do with it. How do you put that into, say, a film or a composite or an electrode? And once you've got that electrode, then the electrical conductivity, mechanical properties, etc., become important. But then there's plenty of standards already out there to look at things such as electrical conductivity and mechanical and thermal. So again, I would then say you don't need a graphene standard for that necessarily. You just need to see a standard that's already used in that industry.
Yeah. Well, along those lines, I'm happy to share with this audience, we announced it last week that the Graphene Council, in combination with the Utah Advanced Materials and Manufacturing Initiative and Composites One, which is the largest distributor of composites, resins, and similar materials in the U.S., we're in process right now of doing a graphene-enhanced composites testing project. And just to be brief about that, but it speaks to what you just mentioned, Andy, is it's one thing to measure the material, but it's another to measure how it performs in a given application. And in this case, we're taking sample materials provided by different producers and even different grades of material from different producers, and we're mixing them with a standard resin system that's widely used in industry. And then we're going to put this against 5 different types of tests, including flex modulus, tensile strength, impact resistance, compression, and others, and going to test the resin system without graphene, the resin system with graphene at different load factors, like a 1%, a 1/2, and 1/10% by weight. And then we're testing it even further at those different load factors in non-reinforced, reinforced with glass fiber, and reinforced with carbon fiber. And so what we're really looking at is, okay, you say this is X material, but how does it actually perform in a given matrix or a given application? And I think that's really one of the next frontiers for us. Once we get past this extremely important characterization, we agree on how we're going to measure the material, but then how do we measure it in an application? And that's when I think industry will become very excited, because industry does not care. I hate to be so bold and make a blanket statement. Industry does not care what we call this stuff. They do not care if it has 1 layer or 10. All they care about is how does it perform in a given application? Is it safe? Is it can you repeat the performance, and how does it perform when applied? And I think for graphene to become a commercial material, we need to move quickly to that stage. For those of you in the academic world, I think you might be more interested in the pure science of it, but it still is interesting to know that what you're doing, which was absolutely critical to advance the knowledge on this material, is it applicable though in a commercial world, so that it can actually see the light of day in products making our world safer, better, cleaner, etc. So I don't know if you have a reaction to that, Andy, but that's a little bit of my take on where we're at with this process.
Yeah, and I think is kind of this whole fundamental of does it do a good job or not in my products is what will essentially earn revenue for companies and therefore be important. And hence, in a way, the terminology and the measurement standards are there to just give them that information so they can make a good decision.
Yeah, absolutely. So we can repeat it and that we're also consistent when we talk about it. Coming back to the metrology, since we still have almost 350 people still listening to us, and so obviously there's still some interest here. There's a question, if you don't mind talking a little bit more, and I'm curious myself. I know we've talked about XRD, which has not been used widely, but I think has some real promise because it's a bulk technique and relatively quick. If you could talk about XRD a little bit more, and then the DLS technique, which is even, let's say, less well known, I think, about quality control process for graphene powders. I think that's quite exciting to hear about. Can you talk about that?
Yes, I mean, so XRD again isn't in the list of those standards there, but I wanted to put it in there as again, it's a powerful technique. We know that companies use it. Again, looking at crystalline, you're essentially looking at the sizes of crystalline materials and crystallites. So we saw in the diagram so if I can find that. You can see obvious changes. Again, the issue around this is sometimes drawing too much conclusion from it. Again, if you look at the academic literature, you'll see instances where something has been controllably changed. So just one measurand of some description has been controllably changed, and therefore you see a change in, say, peak position or peak width. It doesn't mean that you can take a material and then put it in, and we see the same issues with Raman, that you can then put another material in and go, okay, I determine that this is this is a quantified quantity with an uncertainty for this measurand, because obviously that was a controlled experiment, but it does show differences. So again, yes, it's not necessarily as quick as, say, doing an optical technique, but typically it will be on the order of, say, maybe hours rather than days of measurement of many flakes. So yes, so powerful technique in that respect. DLS, again, DLS, you're talking about sort of typically minutes to take a measurement. So again, you see the power in that. You're not usually looking at inline for either of these. We're still talking about offline, but you can imagine having a big barrel of powder and taking samples of that barrel and putting it through DLS in some, also adding it to a solvent, putting it through DLS, and looking at the variation. There are companies I know that we've worked with that do that. The issue around it is that DLS, if you get an instrument, it will generally give you a value. It will give you a value of size.
Okay.
And the issue with that value is not that it's not really validated in any way. Again, it's expecting, say, spherical objects. And again, if you look at things such as nanoparticles that may be on the market, you don't get this broad distribution that you do with graphene. And so you might get, say, a nanoparticle that's provided that's 82 nanometers plus or minus 2 nanometers. You're not seeing that sort of monodispersed sizing of graphene. So therefore, when it skews to a larger size, you might go, okay, here's my 10 micron particles, and actually it's nowhere near when you actually look at it with any microscopy. There's not, the particles just aren't that size.
Right. Well, and I imagine with graphene, of course, especially with the flakes, you have such a high aspect ratio. You've got, a few nanometers in height, but you might have a couple microns across the lateral size. And I can imagine that, that changes the way that reading takes place.
Yeah. So, and again, it's something that just needs to be, the metrology needs to be investigated more in these areas, and it could be very exciting and very useful things, and something that we're interested in at NPL as are others, but it's not something that's really been investigated.
I'm going to try to close off with just one or two more questions here. There was a very straightforward question about the cutoff for what is graphene, what's not graphene. The ISO standard nomenclature has identified 10 carbon layers in thickness as graphene, and then above that would be some other material, a nanographite, if you will. That's from the ISO definition. From the Graphene Council, I can tell you that the vast majority of our member companies are producing material that is 10 layers or less. But it is also to say there is material that is produced, including from some of our producing companies, that is in excess of 10 layers, but it still has definite commercial value it would be considered a graphene material from a commercial aspect. We've seen companies talk about carbon nanotubes now as actually being graphene nanotubes, which might be a bit of a stretch, but the logic there is that, it's simply rolled up graphene, so you can make your own judgment on that one. And then, of course, we have another question here, and I'm sorry, Andy, this isn't directed at you necessarily, but it talks about MaxEnes. The Graphene Council does focus on graphene, although we recognize the interesting thing with graphene, and Andy, do chime in here because I know you have experience with this, is when we start talking about heterostructures or heteromaterials where graphene is one of a 2D material that's used in combination with some other 2D materials, which is another exciting area. And I think coming back to characterization and measurement, we fall back into the same challenges and approaches. So do you want to just touch that briefly about not only just graphene, but these other related 2D materials often, which can also be used in combination with graphene?
Yeah, so again, we've talked about graphene here today, and obviously that's kind of the first 2D material, and we see that as being generally closer to market or being used, but there are other materials. I mean, a good example is boron nitride, that sometimes we actually have people that we've worked with that said, graphene's really good, but I really wish it wasn't electrically conductive. And you're like, well, here you go, here's boron nitride, and it's white rather than black. We do a lot of commercial work with companies on projects and measurement services, but we also do very fundamental measurements. So example, we looked at the fundamental issues of defects in molybdenum disulfide, which is a semiconducting 2D material, and how that varies for Raman Spectroscopy, or looking at with tip-enhanced Raman Spectroscopy. So we are interested in those areas because we see these 2D materials as the next ones coming through. And I always like the term atomic scale toolbox, that you can choose these 2D materials depending on what you want, right? What type, semiconductor, insulator, conductor, superconductor.
I think we could probably be on here for another couple of hours if we wanted to. There's just so many questions. Some of them are quite technical, others a little less so. And I'm going to apologize that we can't address everybody's questions. And I'm just overwhelmed by the level of interest. Again, with more than 800 people registered, we had close to 500 people at one point on the live webinar today. And so I'm going to close with just a couple of comments. First of all, and most importantly, thank you, Andy. I really, really value your experience, knowledge, and insight in this area. And thank you for sharing that with such a broad audience. And I know we will continue to work together collaboratively to advance the frontier of this. So thank you for that. For those of you who are interested in these other commercial aspects of graphene production methods, other 2D materials, etc., we have a wealth of information at the Graphene Council. As I mentioned, we're doing another webinar Thursday on CVD graphene. We did a webinar last week on thermal conductivity and measurement of graphene, on graphene enhanced composites. We are going to do a webinar on graphene dispersion techniques, which is absolutely critical for anybody who's interested in dispersing a graphene in a matrix. You can have the best material in the world, and if you can't disperse it properly, your application will fail. It's a critical failure point for this material, is handling and dispersion. So look for that coming up. And we have tons of resources online by video and recorded webinars, and of course our graphene report, which is a member-only benefit, but it is a pretty in-depth resource. So from that, I'm going to sign off as the Graphene Council. Thank you all for attending. I'm going to send you contact information. Feel free to ask for more information, and we'll try to connect you. And as we all globally deal with this COVID-19 period, I wish everybody to stay safe and continue to work as we deal with that challenge. So thank you again, Andy. Thank you so much. Take care, and we'll sign off.
Thanks, Terence. Thanks, everyone.
Pleasure.